All right, so it's just a short video, and we're gonna watch it, and then we're gonna code it up. So I'm gonna play it. Let me know if you don't hear any sound or anything.
If you can fit a line, you can fit a squiggle. If you can make me laugh, you can make me giggle. StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about logistic regression. This is a technique that can be used for traditional statistics as well as machine learning. So let's get right to it. Before we dive into logistic regression, let's take a step back and review linear regression. In another StatQuest, we talked about linear regression. We had some data, weight, and size. Then we fit a line to it. And with that line, we could do a lot of things. First, we could calculate R squared and determine if weight and size are correlated. Large values imply a large effect. And second, calculate a p-value to determine if the R squared value is statistically significant. And third, we could use the line to predict size given weight. If a new mouse has this weight,
heart rate's 120, BP's 140/90. Hectic first day, but earning my nursing degree on.
then this is the size that we predict from the weight. Although we didn't mention it at the time, using data to predict something falls under the category of machine learning. So plain old linear regression is a form of machine learning. We also talked a little bit about multiple regression. Now we are trying to predict size using weight and blood volume. Alternatively, we could say that we are trying to model size using weight and blood volume. Multiple regression did the same things that normal regression did. We calculated R squared, and we calculated the p-value, and we could predict size using weight and blood volume. And this makes multiple regression a slightly fancier machine learning method. We also talked about how we can use discrete measurements like genotype to predict size. If you're not familiar with the term genotype, don't freak out. It's no big deal. Just know that it refers to different types of mice. Lastly, we could compare models. So on the left side, we've got normal regression using weight to predict size. And we can compare those predictions to the ones we get from multiple regression, where we're using weight and blood volume to predict size. Comparing the simple model to the complicated one tells us if we need to measure weight and blood volume to accurately predict size, or if we can get away with just weight. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Logistic regression is similar to linear regression, except logistic regression predicts whether something is true or false, instead of predicting something continuous like size. These mice are obese, and these mice are not. Also, instead of fitting a line to the data, logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. And that means that the curve tells you the probability that a mouse is obese based on its weight. If we weighed a very heavy mouse, there's a high probability that the new mouse is obese. If we weighed an intermediate mouse, then there's only a 50% chance that the mouse is obese. Lastly, there's only a small probability that a light mouse is obese. Although logistic regression tells the probability that a mouse is obese or not, it's usually used for classification. For example, if the probability a mouse is obese is greater than 50%, then we'll classify it as obese. Otherwise, we'll classify it as not obese. Just like with linear regression, we can make simple models. In this case, we can have obesity predicted by weight, or more complicated models. In this case, obesity is predicted by weight and genotype. In this case, obesity is predicted by weight and genotype and age. And lastly, obesity is predicted by weight, genotype, age, and astrological sign. In other words, just like linear regression, logistic regression can work with continuous data like weight and age, and discrete data like genotype and astrological sign. We can also test to see if each variable is useful for predicting obesity. However, unlike normal regression, we can't easily compare the complicated model to the simple model, and we'll talk more about why in a bit. Instead, we just test to see if a variable's effect on the prediction is significantly different from zero. If not, it means that the variable is not helping the prediction. Psst. We use Wald's test to figure this out. We'll talk about that in another StatQuest. In this case, the astrological sign is totes useless. That's statistical jargon for not helping. That means we can save time and space in our study by leaving it out. Logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method. One big difference between linear regression and logistic regression is how the line is fit to the data. With linear regression, we fit the line using least squares. In other words, we find the line that minimizes the sum of the squares of these residuals. We also use the residuals to calculate R squared and to compare simple models to complicated models. Logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't calculate R squared. Instead, it uses something called maximum likelihood. There's a whole StatQuest on maximum likelihood, so see that for details, but in a nutshell, you pick a probability scaled by weight of observing an obese mouse, just like this curve. And you use that to calculate the likelihood of observing a non-obese mouse that weighs this much. And then you calculate the likelihood of observing this mouse. And you do that for all of the mice. And lastly, you multiply all of those likelihoods together. That's the likelihood of the data given this line. Then you shift the line and calculate a new likelihood of the data. And then shift the line and calculate the likelihood again. And again. Finally, the curve with the maximum value for the likelihood is selected. Bam! In summary, logistic regression can be used to classify samples, and it can use different types of data, like size and/or genotype, to do that classification. And it can also be used to assess what variables are useful for classifying samples, i.e., astrological sign is totes useless. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you have suggestions for future StatQuests, well, put them in the comments below. Until next time, quest on.
So since we saw the video, we're gonna code it up, and I see a chat. This one. Oh, no, that's not my voice now. Okay. So now we're gonna do is we have to code, and I need to get out of the Colab. Yep. in the new share. Let's see. All right, sorry guys. It's trying to be familiar with the Zoom. Can everyone see my Google Colab? Okay, thanks. So now, so on the video, we learned about logistic regression, and from my previous one, the logistic regression one, we actually built a simple model for the logistic regression, and the predictability, the correctness was around 83%, but now we are gonna increase it to around 92%. So what you're gonna do is you have to go to a Google Colab. It's COLAB, and then from here, we're gonna code, and let me know if everyone got into a collab, and we're gonna start coding. So I assume everyone is on Google Colab, and the let's see. So from sklearn data sets import load breast cancer. So what we're doing right now is, in order to do machine learning, we need a data set. And the sklearn.data set contains all the variety kinds of data. And within the data, we're gonna use a breast cancer data, and we're gonna make a prediction by using that data. And from sklearn.model selection import train test split. And the now we're gonna import the function from the sklearn model, and then cancer load breast cancer x cancer.data y equal cancer.target. So what happened is x is the data, the given values of the cancer, and we have to find the numeric values in order to make a correct prediction to match with a y, which is the target. So x is the data, y is the target. And the remember we imported train test split function. Now we're gonna use it in this line. So x train all x test y train all y test train test split x y stratify y test size 0.2 random state 42. And the what we're doing here is so stratify y ensures us to have a good distribution and a proportion among the divided data sets. And the we have made the test size as a 0.2, and that'll make train to test to be 8 to 2 in proportion. The train will have 8 out of 10, and test will have 2, so 8 to 2. And random state 42 is a common initialization in the machine learning, and it could actually be any number, but it's a common initialization. And now we are going to further divide. So x train, x val, y train, y val. So what we're doing is we first made a train and testing sets, and now we're having train and validation sets. So there's a train sets, validation sets, and testing sets. And that's why we're gonna split again. Train, test, split. X train, all, Y train, all, stratify, Y train, all, test size, 22, random state, 42. So now, so from the total size of 10, like train to validate to test will be 6 to 2 to 2. So train will have 6 out of 10, validation sets will have 2 out of 10, and test will have 2 out of 10. So further dividing. And now we're gonna print the size of the matrix. Len x train, len x val. And the if you run it, you'll see 364 and 91. And that indicates there are 364 of them in the training sets and 91 of them in the validation sets. And that actually fits with our 6 to 2 to 2 distribution. So what we did here was basically preparing for training. So we have training sets, validation sets, and testing sets. Any questions so far? I assume everyone is finished and I'll continue. So now we are gonna code the actual logistic regression model. So we're first gonna import the NumPy, which is a very useful tool, library tool for the matrices. So import NumPy as np, and we're gonna make a class, single layer, and the create initialization function, self learning rate. So what the learning rate is, we made it 0.1. So learning rate allows us to not make a large change when calculating the gradient. So if we don't have a learning rate, if we don't have a fixed learning rate, when we calculate the gradient, it's gonna approach to a correct value in a large variation. And this actually allows us to have a small change within the gradient so that there will be smooth transition to our correct values. That's why we're setting learning rate as 0.1. And now we are going to make initialization. So W. And Yeah, and this is all about matrices and finding the best solution. So like for like the matrix, if we have A x equal B, where A and B is a matrix, we're trying to find the x that closely approximates the value of B. And if you took the ICSI 401, this semester I'm taking by Professor Magner. This actually resembles closely with the ICSI 401. So you might find it helpful if you took 401. And the define 4-pass. And the reason why I'm going through all the functions without explaining is because I went all the explanation in my previous workshop. But if anyone has a question, I'm willing to explain again. Z is np the sum x self the w plus self b. Return z. And this is all about matrix. It's all about multiplying matrix and adding matrix together. And now we're going to do backpropagation. So in case anyone has not we're not able to join my previous workshop, the reason why we are having backpropagation is we are calculating the gradient. And by using the gradient, we are updating the values of W and B. And so it's called backpropagation because we're going back to update the values of W and B. And 4-pass function is simply just calculating B gradient 1 times CRR return W grad. And through integrals and derivatives, we can actually validate each steps. Define activation. So z 1 over 1 plus okay. And now we're going to make a fit function, which is the most important one. I mean, not the most, but like important. So x, y, epochs. In epoch speed, we're going to make a 100 loops. Self.w and pick ones. Shape. So what we're doing is we're initializing w as all ones. And the self.b is 0. Random, let's see, 42. And what we are doing right now, the MP random seed 42. So if you're familiar with Java, it's similar with the Java one. So for the seed, it is just an initialization to use a random. And so we're going to use a random permutation in order to mix the index of the data sets. And even in Java, in order to use a random, we have to use a seed. So that's why we're trying to use a random. That's why we're using C that's 42. For I in range epochs loss 0 indexes p dot random dot permutation if that range. So here we are missing all the index, and the reason why we're mixing index is the more, if we mix indexes, the data is gonna be different. So each time for each loop, our single layer will be able to have a new data sets because it is all randomly changed. That's why it will greatly enhance in terms of predictability. If we don't, like single layer is just simply gonna memorize all the data sets, like literally memorize. So by doing the randomly switching indexes, we're enhancing the predictability. So for I in indexes, z self the forecast xi, so z, so we are having z as a after forepass, and the yeah, maybe later in the video I'll pull up my drawing again in order to see how z and e and z and a are being created. So z is forepass and a self dot activation z. And what activation function is, it the value is gonna be negative infinity to infinity. And activation function allows us to have a value between -1 and 1. And error I minus a gradient b gradient self effect xi error. And by calling back propagation, we are calculating the gradient so that we can update the values. Okay, so now this is the part how we are updating the values. The reason why we have 1e minus 10 and 1 minus 1e minus 10, it is because we are using the loss function for the logistic regression. And as I mentioned in my previous video, um, there's a specific loss function which I'll be writing pretty soon. And that is why we are writing 1e minus 10 and 1 minus 1e minus 10. So this is the loss function for the logistic regression. Y I log plus 1 minus y times p log minus A. And the this is a loss function for logistic regression. So this is just a comment. So this is a loss function for the logistic regression. Let me actually erase it. Okay. And the self the losses dot append loss length y. Now we are going to make a predictability function. Predict self x z self dot for pass xi for xi in x return and dot array. So what we're doing in the prediction function is we're actually passing all the data sets as a matrix, like not one by one, but like as an entire matrix. And then it's gonna make a prediction. Define score self xy return at the mean self predict x. And this is it. This is a single layer, and the you can run it. And I see no error so far. And the we got a little more to do, but like let me know if you have any questions or you need more time. Were everyone able to finish it? Oh, working for me. Oh, that's nice. Nice, Brian. Okay, I'll assume everyone is finished. And the okay, let's see. So now we're gonna create the instance of a single layer, just like Java. Layer one, single layer. Layer one, the fit x train, y train. And if you remember, we made a training set, validation sets, and the testing sets. So now we're training our model. Layer dot score x val y. Actually, let me explain this first. So fit, we are training. We're training. And now we are putting in the validation sets. So we're training by using a training set, and then we are scoring. We are seeing our prediction score by passing the validation sets. If I run it, Oh, there's an error. Let's see. Let's see. Box 934 W gradient B gradient self W gradient self that problems. Trace back layer 1 fit back proposition takes 2 positional arguments, but 3 were given. Back proposition. Back proposition. Sorry guys, trying to find the error. I'll be quick. Yeah. Oh, the back proposition. There's only 2 parameters. There has to be an error. So it needs a parameter x and ERR. So what you have to do is you have to run again. And to run, you can click the arrow, click this arrow, or the way I do is click shift and enter. So shift and enter. It's more convenient. And you do shift and enter again for the bottom one. So there should be no error. And now it gives me 91% correctness. So that was our validation sets. And now we are gonna do testing sets. Let's see. Layer 1.fit x test y test. Layer 1.score x val y val. So no. Sorry, layer 1.score x test y test. Layer 1.fit x test y test. Yeah, so now that we have done the training and validation sets, now we are doing the testing sets. And this gave me a slightly better 91.3% correctness. So last time it was around 82%, and this time it's about 92%. So this is about 10% improvement. And the reason why we made an improvement is because the major reason is we switched all the orders in the data sets. The switched data sets in the ordering sets, and we had a learning rate. And the now we're gonna see how the losses are being decreased gradually. remember in the code, we made a losses variable as an array, and we have appended every loss, and the loss is calculated by using the loss function of a logistic regression. Now we're gonna print it out and see how the losses are stored. So as you can see, trying to go up. So as you can see, the loss was initially 8, and then 6, and then 5, and then 4, and then 3, and then 2. And then you can see how the losses are decreasing gradually. Like it is steadily decreasing. And now it's 2. So for each iteration, you can see how our performance is getting better gradually. So for the losses, it was initially 8, and now it is 2. And the losses are gradually decreasing. And what the losses mean, it indicates the differences between our calculated result of y and the actual result of y when the data sets as a matrix is calculated. And this is actually the end of my presentation. So let me know if you have any questions or anything. No one has a question or? Did everyone finish the code or? Uh, okay, I assume everyone is finished, and I'll end the meeting from here. All right, thank you guys. Thank you everyone for joining. And maybe it's the Zoom transition that made less people to join. But thanks everyone, and have a good night.
Good night, man. Thank you.
Yep, good night.